Hello, in this lecture we'll find out the radius of a circle. In the drawing we have a circle. The center of this circle is at this point, point O. We know that line segment AB equals to 6 units. Line segment AD equals to 18 units in its length. And line segment BA is perpendicular to line segment AD. Line segment BC equals to 13 units in its length. And also line segment AB is perpendicular to line segment BC. That is to say, angle ABC equals to 90 degrees, and we also know that angle BAD equals to 90 degrees. And our mission is to find out the radius of this circle. So first of all, we will make a construction from point C. We will draw perpendicular on AD. So here, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. In the next step, we will focus on quadrilateral ABEC. In quadrilateral ABEC, we have 1, 2, 3 right angles. The sum of right angles is 90 degrees times 3 is 270 degrees, plus the missing angle, that is angle BCE. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. I repeat again, in quadrilateral ABEC, this quadrilateral, we know that we have three right angles, therefore 90 degrees times 3 is 270 degrees, plus the missing angle, 270 degrees plus the missing angle, that is actually angle BCE. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here, we subtract 270 degrees from this equation, and we get that the missing angle, angle BCE, it is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. Okay, so the missing angle equals to 90 degrees. This angle BCE, it is equal to 90 degrees. So quadrilateral ABEC has four right angles, and we know that any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral ABCE as a rectangle. Why? Because it has four right angles. Quadrilateral ABCE is a rectangle So quadrilateral ABCE is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to AC. AB equals to AC. But we know that it is given us the question that AB equals to 6 units. According to the rule that the opposite sides of a rectangle are equal to each other, we get that AB equals to AC, but we know that AB equals to 6 units, so from this equation, we will get that AC is also equals to 6 units. AC equals to 6 units. It is actually AB equals to EC. AB equals to EC. So here I write down that AB equals to EC, and we know that AB equals to 6 units according to what is given us the equation. So from this equation, 6 equals to AB equals to EC, we we will derive that EC is also equals to 6 units. EC equals to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that in rectangle ABEC, AE equals to BC. AE equals to BC, but we know that BC equals to 13 units, and from this equation AB equals to EC equals to 13, we will derive that AE is also equals to 13 units. AE equals to 13 units, so we can write here that AE equals to 13 units. It is given us in the question that AD equals to 18 units. It is very easy to see from the drawing that AD minus AE, AD minus AE, AD minus AE equals to ED. Equals to ED. That is to say AD equals to 18 units, AE equals to 13 units, so 13 minus 18 minus 13 is 5. So that is to say ED equals to 5 units. ED equals to 5 units. I repeat again. ED equals to AD minus AE, AD equals to 18, AE equals to 13. Therefore, ED equals to 18 minus 13, that is 5. So ED equals to 5 units. In the next step, we will join points D and C together by a straight line. By joining points D and C, we created the right triangle EDC. In the right triangle EDC, by PT as a version for Pythagoras theorem, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC, therefore the square of the hypotenuse is DC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to ED squared plus EC squared. Repeat again, according to the Pythagoras theorem, in the right triangle EDC, DC squared equals to ED squared plus EC squared. So DC squared, that is the square of the hypotenuse, equals to ED squared. ED equals to 5, therefore ED squared equals to 5 squared, that is 25, plus EC squared. EC equals to 6, so EC squared equals to 6 squared, that is 36. In conclusion, we found out that DC squared equals to 25 plus 36, that is 61. So DC squared equals to 61. We take a root out of this equation and we get that DC equals to the square root of 61. DC equals to the square root of 61. We can write here that DC equals to the square root of 61. In the next step, we will join points B and D together by a straight line. By joining points B and D, we actually created the right triangle ABD. In the right triangle ABD, by PT, by Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. Repeat again, according to the Pythagoras theorem, if we focus on the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse, must be equal to AB squared. AB equals to 6, so AB squared is 6 squared, that is 36, plus AD squared. AD equals to 18, so AD squared is 18 squared. This is actually 324. So in conclusion, we found out that BD squared equals to 36 plus 324. So BD squared equals to 360. BD squared equals to 360, or we can write here that BD squared or DB squared equals to 360 is 36 times 10. Here we'll take a root out of this equation and we'll get that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we'll take 36 out of the root, and we know that the square root of 36 is 6. So inside the root we left only with 10. In conclusion, we found out that BD, the hypotenuse BD equals to 6 times square root of 10 units. So I write it down. BD equals to 6 times square root of 10 units. In the next step, we'll calculate the area of triangle DBC. The area of triangle DBC here the squared brackets is the sign for the area. It means the area of triangle DBC. The area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of triangle DBC equals to the base. We'll choose the base as BC. The base of triangle DBC, the base of this triangle, the green triangle DBC is BC. So write it down. BC is the base of the triangle times the height. As I already mentioned before, the height must create 90 degrees with the base. Point B is on the base BC. Point C is on the base BC. So the only vertex that is left is vertex D or triangle DBC. So from vertex D we will draw perpendicular on the extended BC. We'll extend BC by a straight line, and from point D we will draw perpendicular on the extended BC. We will define the touching point of the perpendicular from point D and the extended BC as F. So according to our construction, this angle equals to 90 degrees, this angle equals to 90 degrees. So because of the fact that from point D we draw perpendicular on BC, on the extended BC, and the perpendicular is DF. DF is the height to the base BC. DF is the height. Okay, now we will focus on quadrilateral ABDF. This quadrilateral ABDF. In quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this angle equals to 90 degrees. So in quadrilateral ABDF, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral ABDF as a rectangle. Quadrilateral ABDF is a rectangle because it has 4 right angles. Okay, I repeat again. This quadrilateral ABDF is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB must be equal to side DF. In rectangle AB, DF. AB equals to DF. Okay? AB equals to DF because of the fact that the opposite sides of rectangle ABDF are equal to each other. But it is given us the equation that AB equals to 6. From this equation 6 equals to AB equals to DF, we will derive that DF equals to 6 units. That is to say, we found out that the height DF equals to 6 units. So the area of triangle BDC equals to BC times the height over 2. So the area of triangle ABC, the area of triangle BDC, the green triangle, equals to the base of the triangle BC that is equal to 13 units, times the height to the base. The height to the base is DF that is equal to 16 units over 2. In conclusion, we found out that the area of the green triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3. So in conclusion, the area of the green triangle BDC equals to 13 times 3. 6 over 2 is 3. 13 times 3 is 39. So in conclusion, we found out that the area of triangle BDC, it is equal to 39 square units. We have a new rule. According to the new rule, rule number 1, rule number 1 states that if a triangle is blocked by a circle, then the radius of the circle that blocks the triangle is equal to so we'll define the radius of the circle that blocks the triangle as capital R. So if this is the circle that blocks the triangle, we are talking about triangle ABC is blocked by this circle. This is the center of the circle. Triangle ABC, this triangle ABC. This is triangle ABC that is blocked by this circle, and we know that the length of side AB is equal to A units, side BC equals to B units in its length, and side AC equals to C units in its length. And the radius of this circle is equal to capital R. Okay, O M equals to capital R. Okay, then the radius of the circle that blocks the triangle, that is to say capital R, equals to the multiplication of the lengths of the multiplication of the side lengths of the triangle, that is actually A times B times C, over 4 times the area of triangle ABC. Repeat again. According to rule number 1, if we have triangle ABC that is blocked by this circle, then the radius of this circle, that is to say capital R, that blocks triangle ABC will be equal to the, that is to say capital R will be equal to the multiplication of the side lengths of the triangle by each other, that is to say A times B times C, over 4 times the area of triangle ABC that is blocked by this circle. So actually we can implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle DBC, triangle DBC is blocked by a circle Therefore, any triangle that is blocked by a circle, what is the meaning of blocked? The meaning of blocked, it means that the three vertices of the triangle touch the circle. Here in this triangle, the green triangle BDC, vertex B touches the circle, actually at point B, vertex C touches the circle at point C, and vertex D touches the circle at point D. That is the definition of blocked. If we have only two vertices that are touching the circle, it is not, the triangle is not blocked by circle. Only if all the three vertices, like in this drawing, the three vertices of the green triangle B, C, D are touching the circle at points B, C, and D, only then we can say that the triangle is blocked by a circle, like in this drawing. Therefore, we can implement rule number 1 in our drawing. According to rule number 1, if we define the radius of this circle as capital R, here the radius of this circle it is equal to capital R, it is OM, then the radius of this circle capital R will be equal to the multiplication of the side lengths of this triangle, that is to say it is BC times CD times DB. That is the multiplication of the side lengths of the triangle by each other over 4 times the area of triangle BDC. I'll repeat again. According to rule number 1, the radius of this circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the triangle by each other, that is to say BC times CD times BD, over 4 times the area of the green triangle BDC. So capital R equals to BC equals to 13 units, CD equals to the square root of 61 units, and DB equals to 6 times square root of 10 units. That is the multiplication of the side lengths of the green triangle DBC by each other, over 4 times the area of triangle BDC. We already found out that the area of this triangle BDC equals to 39 square units. Okay? So here we will divide both the numerator and the denominator of this expression by 13, and we get that capital R, the radius of the circle that blocks the green triangle DBC, will be equal to 13 over 13 is 1. So we left in the numerator only with square root of 61 times square root of 10 times 6. In the denominator we have 4, and we have to divide the denominator by 13. 39 over 13 is 3. So in the numerator we have 3 times 4. Here we will divide both the numerator and the denominator of this expression by 6, and we will get that the radius of the circle that blocks the green triangle DBC will be equal to square root of 61 times square root of 10. 6 over 6 is 1, so 6 will get cancelled, over 4 times 3 is 12, and 12 over 6 is 2. In conclusion, we found out that the area, that the radius of the circle, the radius of this circle that blocks the green triangle DBC, it is equal to square root of 61 times square root of 10 over 2. According to the algebraic identity that the square root of A times square root of B equals to the square root of A times B, we will get that the radius of the circle that blocks triangle DBC, the green triangle, will be equal to the square root of 61 times 10 over 2. So the radius of the circle that blocks triangle DBC, the green triangle, will be equal to the square root of 61 times 10 is 610, and 610 over 2. So the answer to the question is that the radius of the circle that blocks, the radius of this circle that blocks triangle DBC is equal to the square root of 610 over 2. The square root of 610 over 2 in terms of numbers, it is equal to 12.349 units. And that is the answer to the question. I will check it again. Yes. So, in conclusion, we found out that the radius of this circle that blocks the green triangle DBC equals to either square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the question, so I will summarize the lecture. In the original drawing, we have a circle. Inside the circle, we have line segment AB that is equal to 6 units, line segment BC equals to 13 units, and line segment AD equals to 18 units. And we know that angle BAD, this angle equals to 90 degrees, angle ABC equals to 90 degrees, and our mission is to find out the radius of this circle that inside it we have this shape, the shape ABD. Okay, so first of all, we did the construction. From point C we drew perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. So if we focus on quadrilateral ABEC, this quadrilateral, in quadrilateral ABEC we have 1, 2, 3 right angles. The sum of 3 right angles is 90 degrees times 3 is 270 degrees, plus the missing angle that is angle BCE. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 90 degrees times 3, that is 270 degrees, plus the missing angle BC, in total they must be equal to 360 degrees. Here we subtracted 270 degrees from this equation and we got that the missing angle BC equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. That is to say the missing angle is right angle. Therefore, in quadrilateral ABEC we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral ABEC as a rectangle. Quadrilateral ABCE is a rectangle. Why? Because it has 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. AB equals to EC according to the rule that the opposite sides of a rectangle are equal to each other. But we know that AB equals to 6, so we can write here that AB equals to 6. And from this equation 6 equals to AB equals to EC, we derive that EC is also equals to 6. Here, EC is also equals to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, in rectangle ABEC, BC equals to AE. BC equals to AE. But it is given as an equation that BC equals to 13 units. And from this equation AE equals to BC equals to 13, we derive that AE is also equals to 13. Here AE equals to 13 units. Okay? What is the length of ED? From the drawing it is very easy to see that ED equals to AD minus AE. Again, AD minus AE equals to ED. I'll repeat again. AD minus AE equals to ED. AD equals to 18 units. AE equals to 13 units. Therefore, AD minus AE is 18 minus 13. That is 5. So, in conclusion, we found out that ED, this line segment ED equals to 5 units. Okay, in the next step we join points D and C together by a straight line. And we focus on the right triangle EDC. This right small triangle EDC. We implemented the Pythagoras theorem on this right small triangle EDC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. It must be, that is to say, it must be equal to ED square plus EC square. In conclusion, according to the Pythagoras theorem, if we focus on the right triangle EDC, the square of the hypotenuse is DC square, it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to ED square plus EC square. So DC square, that is the square of the hypotenuse, must be equal to ED square. ED equals to 5, therefore ED square is 5 square, that is 25, plus EC square. EC is 6, so EC square is 6 square, that is 36. So in conclusion, we found out that DC square equals to 25 plus 36. 25 plus 36 is 61. So we found out that DC squared equals to 61. That is the square of the hypotenuse. We took out of this equation and found out that DC equals to the square root of 61. So the hypotenuse DC equals to the square root of 61. Okay. In the next step, we join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. We can implement the the Pythagoras theorem on this right triangle ABD. According to the Pythagoras theorem, in the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DB, therefore, or BD, therefore the square of the hypotenuse is BD square. So BD square in the right triangle ABD must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD square plus AB square, or AB square plus AD square. So in conclusion, found out that according to the Pythagoras theorem in the right triangle ABD, BD square equals to AB square plus AD square. That is to say, BD square, that is the square of the hypotenuse of the right triangle ABD, must be equal to AB square. AB is 6, so AB square is 36, plus AD square. AD is 18, therefore AD square is 18 squared, that is 324. In conclusion, we found out that BD square equals to 36 plus 324. 36 plus 324 is 360. So in conclusion, we found out that BD square equals to 360. 360 is 36 times 10. We took a root out of this equation and found out that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take out 36 out of the root, and instead of 36 we can write down 6, because the square root of 36 is 6 times square root of 10. In conclusion, we found out that the hypotenuse BD equals to 6 times square root of 10. Okay. Then we found the area of the green triangle BDC. The area of the green triangle BDC is equal to, according to the formula of the area of any triangle, it must be equal to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So the area of the green triangle BDC will be equal to the base of the triangle. We choose the base as BC times the height to the base. As I already mentioned 1 minute ago, that the height must create 90 degrees with the base. Here, the vertex B is on the base BC. The vertex C is also on the base BC. So, only from vertex D we can draw perpendicular to the extended BC. So, extended BC by a straight line, and from point D we draw perpendicular on the extended BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and the extended BC as F. So here we created quadrilateral ABDF. This is quadrilateral ABDF. In quadrilateral ABDF we have 1, 2, 3 right angles. In any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So the missing angle must be also equal to 90 degrees. That is to say, angle ADF must be also equal, this angle must be also equal to 90 degrees. So actually found out that in quadrilateral ABDF we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral ABDF as a rectangle. What is down here, this quadrilateral ABDF is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB is equal to DF in quadrilateral ABDF. AB equals to DF, but it is given us in the question that AB equals to 6. So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6. So we found out that DF, that is actually the height to the base BC, is equal to 6 units. Now we can find out the area of the green triangle BDC. According to the formula, that the area of any triangle is equal to the base of the triangle times the height to the base that must create 90 degrees with the base over 2. We choose the base as BC. And the base BC equals to 13. So we substitute BC by 13. The height to the base is DF. And DF equals to 6. So we substitute the height by 6. So it is, the base is 13. The height is 6, so the base times the height is 13 times 6 over 2. So the area of triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3. So in total we found out that the area of triangle BDC equals to 13 times 3. 13 times 3 is 39. So we found out that, in conclusion, that the area of the green triangle BDC equals to 39 square units. Okay, then I presented to you a new rule that is actually rule number 1. According to rule number 1, if triangle ABC is blocked by a circle, then the radius of the circle that blocks the triangle is equal to, if the radius of the circle is capital R, then capital R will be equal to A times B times C, that is the multiplication of the side lengths of the triangle, over 4 times the area of triangle ABC that is blocked by the circle. So I drew here the drawing for rule number 1. We have a circle, and in the circle we have triangle ABC. This is triangle ABC that is blocked by this circle. Why triangle ABC is blocked by the circle? Because of the fact that all 3 vertices of the triangle, that is to say vertex A, vertex B and vertex C, they are all touching the circle. Vertex A touches the circle at point A, vertex B touches the circle at point B, and vertex C touches the circle at point C. Therefore, we can say that the circle blocks triangle ABC. And we know that the length of side AB is equal to A units, the length of side BC equals to B units, and side AC equals to C units in its length. Therefore, the multiplication of the side lengths by each other will be A times B times C. So the radius of this circle OM, that we defined as capital R, will be equal to A times B times C over 4 times the area of this triangle, triangle ABC, that is blocked by the circle. So in conclusion, according to rule number 1, we get that the radius of this circle that blocks triangle ABC will be equal to the multiplication of the side lengths by each other, that is A times B times C, over 4 times the area of this triangle, triangle ABC, that is blocked by the circle. Okay? We can implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle, triangle DCB. This green triangle DCB, all of its 4 vertices, that is to say D, C and B, are touching the circle. Point B touches the circle at point, vertex B touches the circle at point B, vertex C touches the circle at point C, and vertex D touches the circle at point D. Therefore, we can say that the green triangle BCD is blocked by the circle. And because of the fact that we have here the green triangle that is blocked by a circle, whenever we have a triangle that is blocked by a circle, we can implement rule number 1. So we can implement rule number 1 in our drawing. And according to rule number 1, the radius of this circle, that is to say capital R, will be equal to the multiplication of the side lengths of the green triangle that is blocked by the circle, that is to say BC times DC times DB. Repeat again. The radius of the circle that blocks triangle BBC will be equal to the multiplication of the side lengths by each other, that is to say BC times CD times DB, over 4 times the area of the green triangle BDC. Over 4 times the area of triangle BDC. The square brackets is the sign for the area. Okay, so the only thing that is left to do is to put the values of BC, CD and DB in this formula in order to find out the radius of this circle that blocks the triangle. That is the only missing variable. We know that BC equals to 13, so we substitute BC by 13. We know that CD equals to the square root of 61, so we substitute CD by square root of 61, and we know that DB equals to 6 times square root of 10, therefore we substitute BD by 6 times square root of 10 over 4 times the area of the green triangle DBC. We have already found out that the area of triangle BDC equals to 39 square units, so we substitute the area by 39. And finally we found out that the radius of the circle that blocks the green triangle BDC equals to 13 times square root of 61 times 6 times square root of 10 over 4 times 39. Here we divided both the numerator and the denominator of this expression by 13. In the numerator we have 13 over 13 is 1, so 13 will get cancelled, and we left only in the square root of 61 times square root of 10 times 6 over 4 times 39. So as I mentioned before, we divided both the numerator and the denominator by 13. So 39 over 13 is 3. So in total in the denominator we left only 4 times 3. And therefore the radius of the circle that blocks triangle DBC, the green triangle, is equal to square root of 61 over 10 times 6 over 3 times 4. Here we divided both the numerator and the denominator of this expression by 6. So here 6 over 6 is 1, so 6 will get cancelled. So in the numerator we left only with 60 square root of 61 times square root of 10, and we divided the denominator by 6. In the denominator we have 4 times 3, that is 12, and 12 over 6 is 2. So we left the denominator only with 2. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC equals to square root of 61 times square root of 10 over 2. According to the algebraic rule that square root of A times square root of B equals to the square root of A times B, we will get that square root of 61 times square root of 10 will be equal to the square root of 61 times 10, all divided by 2. So the radius of the circle that blocks this green triangle BDC will be equal to 61 times 10 is 610. So it is square root of 610 over 2. I repeat again that the radius of this circle OM that blocks the green triangle BDC equals to either the square root of 610 over 2 units, or in terms of numbers, the radius of this circle OM, it is equal to 12.349 units. Okay, thank you very much.